So you need to know if the molecule is symmetrical. If it is asymmetrical, instantly the molecule is polar. Now, the problem is if it's symmetrical, it could still be polar and nonpolar, but you have to focus on who is attached to the central atom. So like linear tends to be a linear is a symmetrical shape. But watch this. I'll draw two linear molecules for you real quick. You don't need to draw them. I'm just going to draw them. Carbon dioxide is linear. HCl is linear. Okay? Oxygen yanks really hard on the electrons. Oxygen yanks really hard on the electrons. This is linear. The dipoles cancel out through symmetry. One yanks this way, the other one yanks equal and opposite this way. Okay? Now, HCl is linear. This is a straight line. There's no other way to draw it. But there's only one dipole, and it's being yanked towards the chlorine. Chlorine is more electronegative. There's nothing canceling this dipole out, which means this region is slightly negative and this region is slightly positive. There's nothing going the other way. So this is a symmetrical shape, linear, but this is polar. Sorry, this guy was nonpolar. Because the dipole, there's no other dipole to cancel this one out. So that's what this is saying over here. So again, this was what I was trying to do right at the end of class. You have your general symmetrical shapes that will be nonpolar, but you still have to focus on who's attached. And then you have your asymmetrical shapes, which is bent and trigonal pyramidal, and these are always polar. There's no way you can get the dipoles to cancel out in either of these two shapes. Okay? So, let's keep going. Now, ionic bonding is something we briefly talked about at the very, very beginning of this chapter. Ionic bonding happens when one atom loses an electron. And when things lose electrons, they become positively charged. They're called cations. And then that's because the other thing actually takes the electron. So in covalent bonding, when we have polar bonds, they're sharing electrons, but sometimes not evenly, but neither one of them is strong enough to completely rip the electron off of the other atom, which is why they're forced to share. Now, in ionic bonding, that is not what happens. One of the atoms is very strong, very electronegative, and is very attracted to electrons and will completely remove the electron from the other element. And when it does that, the other element becomes, when it does that, it becomes negatively charged because it gains an electron, and the other thing loses it. Now, what holds ionic bonds together is that positive and negative attraction. They call those electrostatic forces. Because instead of sharing and holding it together in a covalent bond, one thing loses and the other thing gains, and the plus and minus charge is what keeps the compound together. There's no sharing involved. It's this attraction. You can think of it like magnets. Pluses are attracted to negatives, so that's how they stay stuck together. In ionic bonding, remember ion means to have charge. So for the sake of our periodic table, metals have really, really low ionization energies. What does that mean? They have very few valence electrons and they really easily lose them. They're like, please take my valence electron. So you see your metals on your periodic table tend to be your cations, whereas your nonmetals have really high electronegativities. They have high ionization energies. They're super attracted to electrons, so they easily take in the electrons. Now this creates a perfect partnership, right, with metals and nonmetals. If metals want to lose them and nonmetals want to gain them, then they create this beautiful partnership of one thing losing and one thing gaining, and they create ionic compounds. Now when they form what are called crystal lattices. And kind of if you think about salt, like if you think about just regular table salt, if you were to dump a bunch of salt in your hand, it kind of looks like crystals, right? Now, I want to clarify that NaCl is table salt, sodium chloride. That is the most common salt that you're familiar with. However, most ionic compounds, aka a metal with a nonmetal or a metal with a bunch of nonmetals, known as polyatomic ions, which we'll get to later, are all called salts. So I know you're used to thinking of salt as like the stuff you put on your food, which there's no problem with that. That is a type of salt, but pretty much the word salt is interchangeable with any compound that is considered to be ionic. That means metals with nonmetals. Okay, anything that has positives and negatives can be called salts. So sodium chloride is what I'm telling you is not the only salt ever to exist. There's tons of other salts. They might not be the salts that we eat, but there are plenty of other salts that exist in nature. Okay, now, oh, is this on your end? I think I shared a link on here. Oh, yes. Apparently it's not popping up on mine, but it's popping up on yours. I would like you to take a moment to launch this ChemThink, and we're kind of going to work on it together. I've actually never done this through Pear Deck, so we'll see how it goes. So I want you to be able to click on it. It should be interactive with you, and you're just going to kind of mess around with some salt. Okay, so I'm going to give you a minute. I'm going to mute myself, but I'm going to continue to go through it. And I want you to kind of go through this at your own pace to get through all 27. It shouldn't take super long, but I'll give you about, 3 or 4 minutes to complete this tutorial, please. They're repelling each other. Electrons don't want to be next to other electrons. But positive and negative attract one another. So they will stick together. just kind of weird, but I found it, I hope you found that helpful with understanding ionic bonding as opposed to covalent bonding, because covalent bonding with these Lewis structures is what we've been doing. So then now there's another type of bonding. All right, so there's 3 types of bonding in this chapter so far. Ionic, which is what we just went through. Covalent, which is sharing of electrons. Now, sometimes unevenly, but still sharing. And so let's refresh. Ionic is metals with nonmetals. Covalent is generally non-metallic elements only, nonmetals with other nonmetals. And then this last one is going to be bonding in metals. So metals, right, are just metals attached to themselves. So like a bunch of copper is bonded to itself with other copper atoms. Now bonding in metals is interesting, right? We know some certain properties of metals, but their valence electrons, right? We know metals don't hold on very tightly to their valence electrons. That's why nonmetals can easily take them, right, and create an ionic bond. But because those valence electrons are held so loosely, the fancy word is called delocalized. This word delocalized means they're mobile. They can move freely between other metal atoms. So in metallic bonding, they don't lose electrons. Their electrons just kind of move freely between the other metal atoms. And they call this a sea of electrons. And I also have an animation for this, and it'll be interesting if it works. I've never tried it on Pear Deck. Let me see if I can click on it if it'll work. Okay, oh shoot. It's not going to work. So what I'm going to do is I'm actually just going to reference back to here because I did have this animated. Now it's not going to work on here. Okay, give me 1 second. +2. Okay, so we know that there are certain properties of metals that make them special. We know that they are malleable. What does that mean? You can bend them. Okay, they can be bendable. They are ductile. That means they can be stretched out into wires, right? We use copper wiring for so many things. They have the ability to do that. We know they're super, super hard to melt. This is high melting point. Super, super hard to boil, high boiling point. But we also know they're great conductors of heat and electricity. So now let me see if I can click on this, if it'll work. Okay, they're great conductors of heat and electricity. And I'm about to show you why. Oh no, go back. So look at these electrons. This is what it means that they're delocalized. They don't leave the atoms, but what they do is they move around freely between the atoms. This is why the heat and electrons and electricity flow through them so easily, is because there's so much, the electrons are so mobile, they're not fixed between the atoms, that allows the heat and electricity to flow so freely. So again, they call this a sea of electrons because in metal, so this would be just a bunch of zinc atoms next to each other. Zinc, 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 zinc. And the valence electrons in zinc just like are kind of just, I don't want to say shared, but flow easily between all the other atoms of zinc. They're mobile, they're delocalized, all right? And that's what gives metals all of these really awesome and kind of unique properties. So let me pause. Okay, I'm sorry I wasn't sharing my screen. So just again, you have these zinc atoms, zinc, 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 okay? Zinc has 2 valence electrons. Now, all these atoms are just kind of letting their electrons be delocalized, meaning they don't like fly off the atom, but they move freely between all of the other zinc atoms. So again, metallic bonding. This is why heat and electricity is conducted so well by metals, is because of this these delocalized electrons easily flowing between the metallic atoms. Okay. So again, they call this a sea of electrons, and this happens with metallic bonding, meaning metals bonded to themselves, okay? So now we're going to go back to our presentation, and we're going to discuss hydrogen bonding. Now, I briefly mentioned this with water, Okay, and hydrogen bonding happens because you have a polar molecule, and you have a hydrogen attached to one substance, and it is attracted to in this case the oxygen of another substance. Now these are water molecules. This is a single water molecule, a single water molecule, a single water molecule, a single water molecule, and now we know water is polar, right? Meaning that there's uneven sharing of electrons in a water molecule. So, right, this is oxygen, right? So all of the electrons are being yanked towards the oxygen. All of the electrons are being yanked towards the oxygen. All of the electrons are being yanked towards the oxygen, and every single one of these, right? Because oxygen is more attracted to electrons than hydrogen is. Well, if that happens, that means if the electrons are existing closer to the oxygen, this region becomes slightly negative, and this region under here becomes slightly positive for every single water molecule. So again, slightly positive, slightly negative. The oxygen region is slightly negative and slightly positive. Now what that causes is the slightly positive hydrogen of one water molecule will become attracted to the slightly negative region, which is the oxygen end, of another molecule. This right here is called a hydrogen. Oops, I'll just call it H bond because I'm gonna run out of room. A hydrogen bond. Do not confuse this. So these are hydrogen bonds, hydrogen bonds, hydrogen bonds. Do not confuse this with real covalent bonds. These are forces of attraction that are keeping water attracted to itself. This is a covalent bond. 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 This is not a covalent bond. It's a force of attraction between partially positive regions of one molecule and partially negative regions of another molecule. And this happens because water is polar. Now, water is not the only molecule that's capable of hydrogen bonding. It is the most common one we talk about, especially in here, but it is not the only hydrogen, or it is not the only excuse me, I can't talk right now. It is not the only thing that's capable of hydrogen bonding. Okay, so the last thing we need to talk about is drawing Lewis structures for ions, and then I will be finished. I have until 46 if I'm not mistaken, so please don't bail out yet. Okay, so here we go. We're gonna draw sulfate, and now this isn't much different than what we've been doing. It's pretty much what we've been doing, but now with ions, we have to draw in extra electrons because ions have extra electrons. So look at this is SO3 2 minus, meaning I have an S with 6 valence electrons. I have an O with 6 valence electrons times 3 because there's 3 of them. Now, unlike what we've been doing, 2 minus means I have 2 extra electrons. So again, there's not much difference except for you're going to have to add in the 2 extra electrons yourself. So let's do this. SO3 2 minus. So draw sulfur. Sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. Now I'm going to draw 3 oxygens. 1, 2, 3. Now this is where it can get funky. So draw in your 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4, 5, 6. So I've accounted for all of these so far. Okay. Now you have to bond everything at least once. Otherwise, there's no point of doing this. Now, I'm going to have to split up this lone pair right here in order to cause it to bond. Okay? All right. So I have handled everything. Now, is anything stable? Does anything have 8 or an octet of electrons? And that answer is no. So what can I do? Well, there's actually a couple of things you could do. The first thing I can do is I can create stability by making this a double bond, right? Okay, now you go, well, 2, 4, 6, 8, 10 electrons around sulfur. Can it do that? Yes. Sulfur is allowed to be expanded. It's on the third energy level. It has empty d orbitals. So yes, this is allowed to happen. So I want to go back because I want to, okay. Now, 2, 4, 6, 8. This oxygen is stable. So we're good here. The sulfur is good. This oxygen is not stable. 1, 2, 3, 4, 5, 6, 7. But look it, you can't forget that you get to add 2 extra electrons. Well, golly gee whiz. I'm going to put one right there then. I'm putting a star to implement saying this is my -2 charge. This is where those are coming from, okay? So 1, 2, 3, 4, 5, 6, 7, 8. Stable. What about this guy? 1, 2, 3, 4, 5, 6, 7. Oh, okay. 8. Beautiful. I can absolutely do this. So look at, how many electrons is this? Well, 6 times 3 is 18, plus 2 is 20, plus 6 is a total of 26. So I would always go back and count to make sure you did it right. So I'll circle everything. This is 2, 4, oops, I shouldn't have used that color. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so this checks. All of my oxygens have 8. My sulfur has 10, which is an expanded octet, but that's okay because sulfur is allowed to have an expanded octet. And now the only extra thing, oops, that you need to do is when you have an ion, you must draw brackets around it, and you must put the charge if there is one. So in order to get like full credit, you have to have both of these things. So this is a Lewis structure for sulfite. That's its name. Now you go, well, what's its shape? Well, it doesn't matter. Look it, it's still bonded 1, 2, 3 times. So AB3. And it has a lone pair of electrons, E. This is trigonal pyramidal. Okay? Same type of shape. Now, what might throw you off is, yes, this is a double bond. That does not change the shape. Double bonds do not mess with the shapes. All that matters are how many things are bonded to the central atom and whether there are lone pairs or not. Okay, we're going to do one more. Now, I realize the bell rings at 46. If you can, please stay with me. I know 7 minutes is plenty of time for you to get to your next class, just like it always was. So we're going to do, I'm going to skip something. We're going to do, ooh, sorry, cross this off. We're going to do nitrate, and then I will stop. So ready, nitrogen has 5 valence electrons, plus oxygen has 6 valence electrons, and there's 3 of them. And then this -1 means I get to add 1 extra electron. So obviously nitrogen in the middle, and nitrogen has 5 valence electrons. 1, oops, sorry, I was trying to make this bigger. 1, 2, 3, 4, 5. Whoa, that was a lot bigger. I didn't mean to have that big. Okay. Oxygens. I'm going to put by the lone electrons, right? Shoot. Oxygen, oxygen, oxygen. Now, I'll do those in like pink, okay? Oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now what do? You have to bond everything at least one time. So bond, bond, bond. Okay? The only thing that is stable right now is the nitrogen. Look, it has 2, 4, 6, 8 around it. So my nitrogen's happy. So now you go, well, any suggestions? Well, I need to add 1 extra electron. Okay? Did I? Okay, 1 extra electron. So I'm going to add it to either of my oxygens because they're not stable, right? So this oxygen is now stable. 2, 4, 6, 8. I should have done the electron in red. If you have to leave, you can go. It's okay. I'm recording, so this is my 1 extra electron. And the reason I get to do that is because of this -1 charge. Okay? Now here's a problem. The next problem is this. This oxygen is not stable and this oxygen is not stable. So I am forced to split my lone pair up. You have no other choice but to split it up. So I'm going to create a double bond between this oxygen or this electron and this electron. Now I'm just going to move this electron right here. It doesn't matter. Remember, they're available for any atom in the compound to use. So now I have a double bond. And now I have 2, 4, 6, 8, 9 electrons around nitrogen. Nitrogen is not allowed to have an expanded octet. It is on the 2nd energy level. It is not on the 3rd. So what do? Well, this oxygen is not stable. So this oxygen is, and this oxygen is, but now this nitrogen is not, and neither is this oxygen. So what do you think I should do? Well, I'm going to take this 1 electron. Nitrogen doesn't want it. And this oxygen does. So I'm going to move it. This electron is going to come over here to make this oxygen now stable. I relocated it. So I'll just draw a little arrow so I can show you. I relocated it. Okay? So now look. 2, 4, 6, 8 electrons around nitrogen. 2, 4, 6, 8 electrons around oxygen. 2, 4, 6, 8. 2, 4, 6, 8. Everything is stable. And then because it's an ion, you must put a bracket around it and you must put the charge. So this is the last thing from this chapter. These are called Lewis structures of ions. And so this is where we will finish. I will put your homework up in a little bit. I'm going to stop recording real quick.